welcome to another coding session with Bangalang. Coming along nicely. Looking at our features list. The next one that was on the list at the end of the last session was query core count, which is where, for our broomstick, we want to spread work across all the cores, right? That's kind of the idea if we're running on the CPU with the broomstick. But I just have this hard-coded worker count of 8, and I've got this to-do to say, let's figure out how many cores the kernel has, and that way we can optimize, because that's what we want this number to be. Another side note, I watched a video with Casey Muratori. He's great, by the way. Highly recommended. If you do what I do in this broomstick, when I'm running on the CPU, I just take the workload, divide it into 8, and then enqueue 8 tasks to deal with all the work. Which would work nicely if all cores were created equal, but they're not. Often your CPU will have a couple of performance cores and then some, what do they call them? I don't know, like economy, I don't know, not so performant cores. So if you split the work equally between all of them, the performance cores are probably going to soak it up and get it done quicker, and then they're just going to sit there waiting while the other slower cores do the rest of the work. So it's probably better to divide the workload into small chunks. Ideally small enough that the memory of the chunk can fit into the CPU cache, and then schedule all those chunks. So then the higher performing cores can grab more chunks, and I think overall you get a bit of performance. I think there's a few things where when we do broomstick on the CPU, it's slower than the GPU, which is what I expected, but I do think the CPU has there's a few things about the CPU broomstick that are not so great. Anyway, that was just like a total aside. What I was really getting at, which is also an aside to what we're going to do today, is that this work account is hard-coded at the moment, and I wanted to query it from the kernel. Well, that was my idea. I thought that would be a syscall to get this information. I thought, very easy. When I looked into it, it turns out it's actually not so easy. It turns out you actually have to look in, I think it's proc/proc-info. Maybe I can... What is it? Well, I know I've done it before. No, not like that. Proc-info. CPU info. Okay, anyway, so there's this file, and it contains one of these entries for each, I don't know what to call it, logical core on my system. So you can see this is processor 15. There's 0 indexed, so there's actually 16 of these listed in this file, which I guess is why when I go to my system monitor and look at my resources, it says that I have 16 CPUs. But if you look closely here, you can actually see that CPU cores says 8, and this one says core ID 7, and if we go up to this one, it also says core ID 7, and this one is 6, this one is 6. So actually there are 8 cores, 8 real cores on my system. So to get that 8 that we were talking about, basically we need to parse that file and grab the 8 out in whatever way we choose, which is obviously Linux specific, but we already have a bunch of Linux specific code in here. generalizing so it works on Windows is something for a later day. So all of that explanation is basically to say that I kind of identified these things as some nice things to have when it comes to like actually parsing this file that we don't have right now. So let's try this list. I think the most difficult one is dynamically sized arrays, which I'd actually forgotten we couldn't even do yet. But if we go back to our main file, there's an example here, you know, where we allocate on the VRAM and we use this because we can't use a variable. So I want to use a variable. And another thing when I was looking into this and thinking about it, I had set it up so that you had to allocate a pointer, but it feels a bit weird. Because then it's like, oh, I'm allocating a pointer to this, so I should only get a pointer back, right? It should only allocate 8 bytes because that's how big a pointer is. But that's not actually how it's working. It's actually allocating this and giving you a pointer back. And I think this whole thing is confusing, so I think I want to take that off. I think this makes more sense. So now I'm allocating an array of vec4s of this size in VRAM. This is actually going to return a slice, because if I return an array, well, first thing is that we need the pointer. We still need the pointer. So an array type doesn't actually contain a pointer in my language. I guess it kind of is a pointer, but anyway, we want the pointer and the length because we still want to be able to do bounds checking. So this is actually going to return a slice. That's my idea. And if we wanted to like allocate just like a single float, then this will actually return, so this variable will actually be a pointer to an F32. So this here is basically the same, you know, in other languages. It's like you're doing something like this, you know, new F32, then you would expect to get a pointer back. This is just my version of it. And the special case is that if you do an array, you get a slice back. That's kind of the change that I'm thinking of doing, alongside also allowing this to be a variable. Whew. Okay, a lot of explanation so far. We're 8 minutes in, we haven't really done anything yet. So this vertex count, let's allow this. This is the first thing. So this is a grammar change, because right now the type primary allows us to declare arrays, but inside the square brackets it only allows a number. So we want to change that. Where is it? Here it is, this number. We want to change that to a right-hand side expression. So it could be any expression. And this reminds me, actually, we have a deficiency in our grammar, because at one point for a right-hand side primary, we changed this whole mess here, which is like our way of saying that we can index and we can slice things. And we did it on the right-hand side, but not on the left-hand side. The left-hand side should be the same. And if we go to parsing, parsing of a primary, we should see, yeah, we're right here because I was looking at it before. This is where we're in the square brackets. And so it says, you know, if we're dealing with a type primary, do this special thing, otherwise do this. So it is the same for left and right hand side. And it should be the same. So let's grab this code if I can find it. Here's the square bracket. So I guess it's like everything within the square brackets should be the same for left hand side, which has the square bracket here and here. It's a big ugly mess of a grammar, that specific part anyway. I really don't like. It takes up a lot of space. Might even make my own production for it at some point or something, because it kind of confuses things. But anyway, now the difference we actually made was a right-hand side expression in the type primary. So if we go back here, this is when we have a type primary and we're dealing with square brackets. So this is saying if we have a number in between the brackets, then parse it. But now I think we need to change that to say, like, if we don't find another closing square bracket, that means that we have an expression here. Or we should have an expression. So let's parse the expression. So now we can have any expression in there. Cool. So type checking will have something to say about that. Yeah, there's quite a few things here where I'm assuming that to be a number because we've restricted it. And yeah, quite often I'll get parsing to do a lot of the heavy lifting, making sure that the structure is correct. And then in type checking, I just assume that it's already correct. But if we go to type checking at primary, so we're talking about types here. Yeah, it's only for types that this is different. So actually, this is when we're declaring things that we provide a type. Like in most situations, this still should be restricted to a number. The only case where it should be allowed to have a variable is if we're using a dynamic allocator. If we're allocating on the stack, this should still be a number. If we're declaring a struct and a member of the struct is an array, that should also be just a number. Yeah, so I think assignment is where we kind of need to handle this. This is where we have like a new, yeah, this is where we're saying that we're declaring something new using a dynamic allocator. And this is where previously I had said you have to use a pointer. So let's take that away. I'm still going to say you can't assign because what we do is we actually generate some AST that makes it an assignment. So here we just have a left-hand side. We don't have equals something. And here is where we actually add. So this is an assignment node. So this is the equals, and then this is the something. I think we're going to take all this source position stuff out. I don't think it's really actually helpful. So I create an allocator node, which is basically a call node of the allocator that we want. This is a bit messy because it assumes that we have memory imported, which is why there's this here. So we don't have memory imported, then it'll say, I don't know what that module is. And then we say that the parameter to that allocator call is a number that we don't know yet. And we figure that out in generation, but we'll get to that. So the first thing is, maybe even up here, I want to say if the thing we're allocating, so I think we have the type node, right? LHS type node. If the thing we're allocating is an array, where are we? So if we have this, we're saying we're allocating an array. Yeah, that should make it an array. Okay, let's just call it an array right now. I have thoughts about whether it should be a slice, but parsing has determined that it's an array. We want to say, actually, this should be a slice. Slices, so an array type node has two children. The first one is the type of thing being the type of the element, and the second child is this expression here. A slice should only have one child, so I'm going to resize the children of this to be just one. But before we do that, we want to save that, I guess it's the length expression node. I guess it's a pointer, we can make it. So before we do that, we want to save that. So that's the second child, like so. So we've saved that length because we're going to use that later on. And if it's anything apart from an array, then, like I said, this is going to return a pointer, right? So we need to wrap this type in a pointer node, so, or reference node. Like so. So we create a reference node. For its children, we add the type that we had, the type that we're allocating, and then we do an assignment. So we say that that is actually the reference node now. I think that's it. So now we've said that this is a reference node containing what it used to be. Okay, so this is kind of our transformation sorted. Now down here, we're creating this allocator node. So this is where we're going to have to get a bit funky, because this just returns a pointer to some data, which is great for this, but not for this. For this, it needs to return a slice. So what I'm actually going to do is I'm going to say, if we're talking about a slice, we do one thing, otherwise we do something else. I guess that's equals equals. And in this case, I guess I'll call it a right-hand side node. I'm going to create a compound literal, because that's how, sort of be kind of like this. Raw equals VRAM allocator with the size. Length equals the size, Well, length equals vertex count, and this will be vertex count times size of vec4, right? That's how much memory it needs to allocate. So effectively, we want to turn it into this. That's the result, right? But the shorthand for it is this. So we need to create some AST that does that. So we get a compound literal. And then the first child of that needs to be, well, the children of a compound literal are assignments. And then the first child of the assignment is the left-hand side, which is an identifier. An identifier with the value raw. Raw assign, I don't think it really matters, but let's put the values in correct values. raw, assign, and then on the right hand side, this is kind of like our allocator node. That's what we need here. But it's not just going to have a number. Let's cut this part out. So this is kind of our allocator node, which is a call to memory.allocate VRAM, but we haven't provided the parameter yet. So here we're going to put allocator node. And we'll finish this off later. Let's just do the length as well. The length equals, I guess, the length expression node. So we'll evaluate that node to get the length. And this raw will equal allocator node, and an allocator node should have some children. Maybe we could do that up here. See, like here we just give it a number, which we figure out later. We'll get to that soon. This is when we're just allocating a single thing. But here, I actually want to send in a multiply. If you remember what we did just before, over here. Oh, what? It was like this. So this is that length expression node, and then the size. This is the thing we get out of generation. So we have a multiply node. We should have two children. The first child can be the length, and then the second child can be the size. Or let's do it the other way around. So the second child is the length, and the first child is like just this number literal guy that doesn't have a value yet. So the size, this should be the size of an element in the array, and then this is the length of the array, or slice. So we prepared the allocator node before we insert it. And here we add the allocator node to the node, but here we say the right-hand side node. Okay, so I think that's kind of the AST that's correct to represent this. Or in this case, we're just representing, you know, it's a lot simpler. We're just representing this for this case. I think we've done that. So let's try generation. I'm sure we're going to get some errors when we try to run this, but let's try generation. And I'm remembering that we need to restrict things. Like we should not allow any variable to be anywhere. We need to, maybe let's do that before we get to generation actually, while it's still in my head. So if we're doing a heap, and we have a slice, this is where we could have, this could be let's make a utility procedure that's like just checks that we're only using number literals. contains a non-fixed size arrays. And we can say this should be a type node that we pass in. So if type node.type equals array, and the first child, type node children 0 dot type is not a number literal, that means that we have an array that's not fixed, right? What's wrong here? This should be value. That means we've found an array that doesn't have a fixed size. And then we need to recurse, because if we have a struct, is it only in the case of a struct? I guess if it's just if we have a struct, then we need to recurse. Well, no, like each member of a struct. So maybe we'll just straight up recurse. I don't think we really need to restrict it. So for all the children, if we find a child somewhere in the tree that satisfies this, then we return true. And if we never find anything, then we say false. So this will tell us whether anywhere in the type, could be a very complex type, there is a non-fixed array. So in the case of dynamic allocators, if we have a slice, well, because we've converted it to this slice, right? We've taken this out, right? Because we resized it. So this is no longer an array with a dynamic size. It's a slice. So the type should be sorted. So I think we can just say we can just make sure that left-hand type node does not contain. It should never contain those. It's a bit easier than I thought. Cannot let's say type blah cannot contain non-fixed, what did I call them? Array sizes. And because that's a type, let's go type name, left-hand side type node. What's wrong with this? Oh, because I changed the name there, but not there. And then we recurse. Okay, so let's actually test that. So if we take off this stuff, and we look at this guy here, and I say, I guess it's valid here. Yeah, the only way I can think of is like if we say we want to allocate a struct, which is a member foo, which is and the member foo is this. That should fail. Oh, we have the tests running. Let's disable them because they are slow. Got a segmentation fault. Type check compound literal. The type node is null. Because compound literals, see, they take the type from the expected type, and if you don't provide an expected type, they don't know what they are. So actually that's kind of sucks that we just get this crash. We should probably provide an error. Yeah, so I'm saying if that's probably what I should do is say, if I go like that, take that condition off there and just have it here. So if we have a compound literal, then we need to know the type we need to know the expected type. So if we don't, then let's say, I think I have like cannot determine. Could not determine type of. Could not determine type of compound literal. I think that's fine, just like that. So hopefully if we run that again, we should get that error. So expression. Oh, this is generation. We got the generation. Where's my error? I should have failed type checking because we had a compound literal and we didn't have this. Yes, his could not determine. This doesn't have all return. Okay, we don't have file information because this is like made up. All these nodes are made up, so there's no file information for them. Okay, could not determine type of compound literal, that's correct. So we need to pass on the left-hand side type node, so it has something. Now we get an error, still in type checking. So we're type checking an assignment where the left-hand side is triangle data. Looking at the right-hand side, we're looking in the compound literal. The compound literal has a call in it, which is the allocator call. So we're looking at one of the parameter of the call, I would assume. Yes, the parameter of the call. And it's a multiply node, but it does not have a left-hand side. Did I mess that up? Because this is actually this child. That's child 1, because we've already added a child to allocate a node. Now we add a second child. And we want to make sure that these are children of this one. Well, that these are children of this one. I think that's what happened. Types I32 and I64 are not compatible. Where's my source code? Oh. I think allocator is expecting an I64. Well, that seems to have solved that one and got a new one. We'll have to fix that up at some point. We'll have to have like an auto conversion like we do for indexing. Make a note of that. Okay, so pointer, okay, so also I think what's going on here, the pointer to, this is a vec4, but the allocator procedure returns a pointer to a U8. But I think what we can do is just say for the allocator, we can give it the directive danger untyped. So that'll mean that the return type of this allocator call is ignored and it will just use this type. Okay, I think we're getting somewhere. Which assignment are we looking at? I just want to double check. We're still on triangle data. Okay. Looking at the compound literal. Child node of the compound literal. Assignment statement has no children. Okay, maybe we messed up the AST a bit more. Okay, yeah, the same kind of thing. These need to be children of this assignment, not this assignment. Try that again. I64 and I64 are not compatible. That's a bit strange. I have no idea where that's happening. So, well, that'll be type check expression. I know that. This is it, and I think there's this one. Those are the two places where that error can happen. So then we can check the two different types. So this is in compound literal. We're looking at the length. So we're trying to get the length, which should be an I64, yeah. The type node is an I64. Yeah, I thought it might have children. It has procedure as a child. Okay, the expected type node is an I64 that does not have children, which is what I would expect from an I64. So why would type node have... So this compound literal, the length, so that's this guy, the length expression node. Let's close some of these. And because it's this conversion, but this, so the type node of this call should be just I64. I don't know why it would be more, unless when I do type checking of a call. So this is where the procedure node is a type, so that's where it's a, because this is a type. So it's calling a type, which is how I do conversions. Where are we? Call. So in that case, we add procedure node as a child of the node, and that's how we give it its type information, I think. But then later we get procedure node and we add all this to it. So I guess this is, I thought that when I copied this across, it would kind of be disconnected because we're dereferencing and making a copy. I didn't think that modifying the children here would affect the copy that we put into here, but I guess it is. Let's check that. Okay, procedure node is, okay, so this is a different one, but it should still show the point. Yeah, so it's just an F32. That's what I wanted to have, just as the type of the call. And then if we go here, so now procedure node has a child, which is procedure, which makes sense because it needs to have, although it is a type, it needs to have type information, which is the procedure. So now if we go to node children, well, it would be the last child, wouldn't it? Does it really have that many children? 3. Oh, because it has one, one is the procedure node, one is the parameter, and then the third one is the type. So then if I say, just give it some sort of unique name. F32, no children. I-64, no children. Oh, this time it does have children. Oh, it's the second time we come through because this has been modified now. Yeah, I think there's a few places like this where I'm just making a mess in the AST and I don't know. I think I need to actually print out the AST, and that's one of the things I have written down, to be able to print it out so I can just like look at the AST and make sure that there's not a mess somewhere where I'm not expecting it to be. For our purposes today, I think it's easy enough that we just go, we just say that it's a type and the value is the procedure node value. Just to make sure it's like just a very clean little thing, but really we need to, this is a bigger problem that we need to sort out. Okay. So now we have some assembly issue, which makes sense because we haven't done anything about generation yet. Oh, but we should have got an error here because I added that type checking. This should have tripped. Oh, but it's the second child. The first child of an array is, like I said before, it's the type of the element in the array. The second child is the length expression. So we go like this. It's a bit weird because we get the converted type. So you look at this and you're like, I don't see any issues. Oh, wait a minute. This is line 31. This is this one. Oh, it should be if contains. That's when there's a problem. I have my condition round the wrong way. Okay. So now we see that if we have a pointer to a struct, and this does say vec4 for slice, which I do find a bit funny. It's like a slice of vec4s when really it should be an array of vec4s, right? I don't see that that should be getting changed. So I'm a bit confused about that, but it is, yeah, so actually, LHS type node, that's what we just checked. Ah, well, probably type name. Type name is probably also assuming, if we go to array, yeah, it's just getting the value. It's assuming that it's a number. So if we get the expression node, and we say if it's a number literal, then we just get the value. Otherwise, we'll put like a question mark. I think that'll do. Let's call it a length expression node. That's what I used out elsewhere. And we'll put that in. So then we should get a question mark. There we go. Cannot contain non-fixed array sizes. Put a question mark there. Good. Whew. Okay. So if I just change this back to what we had, should pass type checking. Okay, but assembly fails. Great. We're getting there. Assembly, generation, assembly, yes, but generation. This is where we handle the dynamic allocator. So at the moment, we're assuming this simple structure. We're not looking at this. So I think again, maybe I'll go like that. And we'll say if the thing that we are allocating is a slice, then we need to do something different. So that's the size, which I think should actually just be the left-hand side type node. Right? Because we wrapped it in a reference. So this should be a pointer type, and we should get the size of a pointer. Ah, no, but we don't want... No, we do want that because we don't want it to be the pointer. We want it to be the thing pointed to that we're allocating. Okay, all right, I stand corrected. And here we want the, like the, it's the element size. So here we have the left-hand side type node, which is a slice. So this is also, yeah, it's also the first child, which should be the type of the element. The tricky part is where to put it. So we have the right-hand side node. It's actually in the allocator node up here. So the first child of the right-hand side node and the third child within that, so it's 0, the indexes are 0, 2, and then we're in the allocator node. 0, 0. What did I say? 0, 2, 0, 0. I'll be very surprised if this doesn't mess up in some way. Okay, here's some assembly issues. I was expecting the compiler to crash, to be honest, so that's better than I was expecting. 2, 2, 7. Okay, so there's nothing there. So we guessed wrong. I'm curious if we go to the next one. So the parameter getting passed to VRAM is a 4, which is right. That's the size of an F32. Cool. And if I say blah F32 equals 42, foo equals my float times blah. I just want to check this. I think it should say like they can't do that. Yeah, because the first one is this one's a pointer. Yeah, that's what I wanted to see. Okay. Yeah, so this allocation I think is correct. Calls allocate VRAM. The return value gets put in R12, which then gets copied to the top of the stack. The return value should be the pointer, which is what is allocated here. So this one, I feel like the main problem is that that's not right. So what is that? Here we have a conversion to 64-bit plus 60. So 40, 60. So plus 60 is before all those. So that's just an assignment, right? Oh no, yeah, it's this one. Yeah, so vertex count. Yeah, so vertex count gets converted to an I64. Then we want to put something else in R12 and multiply them together. So the thing we want to put there is the size of a vec4. So I think what that means is that we did not calculate this correctly. We didn't put it in the right place. Let's have another look. Oh, wait a minute. I think I know, because within the allocator node, so RHS node is the first, so 0, 2, but then within allocator node, there's 1, 2 children. So this should be index 1 and then index 0. So it should be 0, 2, 1, 0. Let's try that. Okay, my computer is not happy at all. Is it gonna let me? Okay. I don't know how the recording fared then. I'm getting a wild delay there. So let's see. I might have to fix some stuff up there, but that just like really messed everything up. But that is the size of a vec4. 4 times 32-bit floats. So 4 times 4 bytes, 16 bytes. I have a hunch. Let's just get rid of this guy. Okay. Now it's working, slowly, but working. So that's kind of cool. That allocator worked. I think I noticed this before. We don't need that. And we don't need to slice it anymore because it's already a slice. So it's working. But if I introduce this, it does not. At least that time it didn't like crash my computer almost. So why would that be interfering? I know the VRAM, yeah. when we allocate VRAM, maybe it does do something. Yeah, so we bind the array buffer. I don't think we ever actually do that in our normal code. We just, because it happened to get bound implicitly by this, it worked. So we might have to explicitly bind it. So if we get the first allocator name, so that should be this one. Yeah, there we go. Okay. Cool. I'm kind of, wow, we got to do that in under an hour. That's impressive, I think. This one seems like a little bit more work. Slice comparisons. Yeah, so when we compare slices, right now, it's comparing the slice object itself, which is to say the pointer and the length. So they would have to be two slices of the same length pointing to exactly the same memory. Whereas really, it should be like an array comparison, you know? It should be comparing the data in the memory being pointed to. So I think we need to fix that up. And then that way we could do like an easy string compare. That's what I wanted it for. But I think that's a bit too much considering we have like not much time left. I think a char literal and atoi are not too bad to do. I'm actually still kind of like surprised that we managed to pull that dynamic array sizing off. I think that's pretty sweet. So just to like check, so if I try to do this not in VRAM, I should get an error. Oh. Not what I was expecting. Types are not compatible. Okay. I don't really feel like fixing that right now. I mean, the fact that type checking throws an error is good. I would prefer that it said, hey, you can't use dynamically sized things because you're not using the right allocator. Oh well. Instead of fixing that, get better error when omitting, I'll just put a message because I feel like doing something else right now. Yeah, I want to do that char literal, right? I think that sounds more exciting. So that'll be a grammar change. We have a string literal. Let's say char literal, which would be with single quotes. So single quotes, and then something that is not a single quote, but not multiple of them. Why do I guess I put that in brackets for clarity before. Let's just take the brackets out. Yeah, I guess with this one, it's in for clarity because this is confusing as hell. It's like multiple not double quotes. And this, which is also, this is not very great, but this is saying single quote, then not a single quote, then single quote. That's a char. Okay. And where do we have string literal? I think the only place is like here. Char literal, string literal. Okay. So a right-hand side expression can now hold a char literal. We need to be able to parse them. Well, we need to be able to tokenize I don't think we've ever used a single quote. We don't have a token for it anyway. So we have we don't need a token for it. It's like we have, where do we have our string parsing? So that's comments. Here we go, that's string. So let's put it before string. So if we find let's get rid of this. If we find a single quote, then we don't need to do that. Then we can just say next rune. It's a bit different to these other ones, because it's got a fixed size. And then we'll say peak rune does not equal single quote. And what if it does equal a single quote? How do we throw errors here? Is that where we just do this false business? I think it's just this. So if we peek and we find, I guess we don't need a peek. If we grab the next rune and it's a single quote, then we have trouble. And then again, if we grab the next one and it isn't a single quote, then we have trouble. So now we know we have single quote, not single quote, single quote. Weird. And I think this whole thing works, but now we call it a char. I kind of want to change them to like literal, didn't I do that? Maybe it was only, so for tokens, then there's like AST. Yeah, Boolean literal, I made them all literal. I guess maybe they don't have that meaning yet. If I go like that, it does let me just do char. Okay, yeah, because I think Odin doesn't use the keyword char, it uses rune. Okay. So this is our char. I think that means we've tokenized the char. And in parsing, we parse a primary. We should be able to find a string literal. Let's just copy this and say char, and only right hand side can contain a char. And so we'll call that char literal and grab the value from the token. So we do need a char literal. Token type. So, okay, so I think we've tokenized and parsed in the correct place a char. Now in type checking of a primary, I think this should be pretty easy too. Here's all our literals. Char literal is like, I'm gonna make a char identifier. I think it's just gonna be like, it's just a byte, right? I mean, at some point, I don't really care about it right now, but at some point we're probably gonna have to support UTF-8, which means that some characters can be more than 1 byte. But right now I'm just gonna make it an alias of byte. for simplicity. So if we go to globals, let's just say a char is a byte. And because I like my colors, what's our types? Here we go. Char. Beautiful. So it's just a byte. Just takes on the type of a byte. That's fine. And so I think that's all we need to do for type checking. And then when we go to generation, a primary. So here's our literals. And depending on different types, there's different things. But I think for us, I think we can just do it immediate. I was looking into this. I think you can actually just do an immediate. So you can have like a character just embedded in the assembly instruction. I don't know. The one place that we have which this could be useful is in our standard library in strings. Yeah, this I to A procedure. See, I did like this, but I should be able to just go like this now. What? Oh, that's if we had a 0, if it was only a 0. So this is a minus. Yeah, so those are the three. I think that's the only place that we actually wanted to use literals right now. And it works. We get reasonable FPS. Wow, that was actually not so bad. So if I go here and then like at the top of the file, and say I want a negative number, just to check, because here, you know, we have like this negative character. And it printed out correctly, negative 42. Cool, because I to A, yeah, I to A is what we're using to convert this number to a string to get printed. So I think that's character literals. We're at 1 hour and 8 minutes now. There is A to I as well. I feel like that's not going to take too long. Let's take a stab at this. Maybe I regret this, but feeling overly confident. So A to I will take in a string and return an I64. And I think we'll start from the end of the string and work backwards. So we start off with an integer that, well, let's call it result, hey? So we start off with just a 0 integer, and then for each character in the string, let's say index well, the length will be an I64, so let's call it I64 equals value dot length -1. That'll be the last character. Our index is greater than or equal to 0. Index minus equal to 1. So we go backwards. we'll have a factor, which is an I64 of 1. So then we'll say result plus equals value index, and then here, you know, we added 0 to get to 0, so I guess we will like minus 0. So that should give us a byte. So that should give us a U8. And result is an I64, so we're probably going to have to cast it to I64. So it's actually, and we can multiply that by the factor. And then we say factor times equals 10. So then when we go, so we're starting from the lowest digit, which would just be, you know, times 1. And then the next digit should be times 10. Next digit should be times 100. So that's what this factor is doing. And if you pass in something that's not a number, you're going to get some weird shit coming out. But we need to deal with the minus sign that would be at the start. So let's say if index equals 0 and value 0 equals the minus sign, then break. Don't add that on. If there are minuses, you know, yeah, like I said before, if the string is malformed, you're just going to get some stupid result. I'm not going to do checks. I'm not going to check for you. Just make sure you don't do that. I'm not going to babysit you. So now we do the same check. We say, you know, if there was a minus sign, then we say result is negated. Like so. I think that's A to I. So how can we check that? I guess we can do like an os.exit. Let's comment all that out. Don't need any of this either. All we need is OS. So we can do an os.exit. Oh, we need strings. Strings.a to I 42. It's expecting a U8. So let's convert it to a U8. Wow, pretty sweet. But if it's a negative, yeah, 214. It'll give some weird number. So, I mean, we could, I guess we could do this and then convert it back to a string and print it out. So it should be negative 42. So we have the number. I guess we can just do it straight there. So we go from string negative 42 to a number and then back to a string. And we should get negative 42. Nice, nice. Pretty happy with that. Cool to get some nice wins at the end here and not to have like ruined everything. It's always nice not to ruin things. Okay, so let's just run that, make sure everything's cool. Okay, So I think I'm pretty happy with that. We might be able to pull those two off in the next session. We're at an hour 15. I'm happy. Okay, enough for today. Thanks for stopping by. Have a good one. Ciao for now.